You're holding a pencil. Ordinary yellow, probably chewed at the end. Now look at a diamond. Maybe on someone's finger right now. Maybe in a jewelry store window worth $10,000. Here's what nobody tells you. And I mean nobody. Not your science teacher, not the jewelry store, not anyone. These two things are made of the exact same material. Not similar material, not chemically related material. The same, single, element. The pencil in your hand and the diamond on that ring are both carbon, just arranged differently, which means right now you are holding a diamond. You just don't know how to rearrange it yet. By the end of this video, you will. And what you learn will make you genuinely furious about how much people pay for diamonds. Stay with me. But here's where it gets complicated, because turning a pencil into a diamond isn't as simple as squeezing it really hard, even though that's basically what you eventually have to do. Let's go back to the beginning. Way back. You're standing in a field 10,000 years ago, barefoot, nothing around you but dirt, rocks, and the problem you've been handed. Your mission is to make the hardest, most valuable material on Earth out of something a child uses to write their name. You look around. The good news: carbon is literally everywhere. It's in every living thing, every dead thing, every piece of coal, every breath you exhale, the soil beneath your feet. You are breathing carbon right now. Carbon is the fourth most abundant element in the entire universe. You will never run out of it. The bad news is that carbon is deeply, stubbornly indifferent to what you want it to become. Left completely alone, carbon arranges itself the way a teenager keeps their bedroom. Loosely, flat, with absolutely no structure and zero ambition. Those flat, stacked layers of carbon atoms that slide lazily against each other, that's graphite, the gray stuff in your pencil, soft, slippery, leaves marks on paper, about as far from a diamond as you can imagine, while being made of the exact same atoms. Now here's the part that should make your brain stop for a second. A diamond is also just carbon. Every single atom inside a diamond is the same element as every single atom inside your pencil. The only difference, the only thing separating a $10,000 gemstone from a 40-cent writing tool, is how tightly those atoms are packed together and the shape of the bonds between them. In graphite, carbon atoms bond in flat hexagonal sheets that stack loosely and slide. In a diamond, each carbon atom bonds to four others in a rigid three-dimensional lattice that locks every atom in place permanently. That locked lattice is the hardest natural structure ever discovered. Nothing scratches a diamond except another diamond. So your problem isn't finding carbon. Your problem is convincing carbon to stop being lazy. And to do that, you need to recreate conditions that naturally exist only 100 miles below the Earth's surface, where temperatures exceed 1,300 degrees Celsius, and the pressure is so intense it would crush you into a smear before you could even register what was happening. You need to build the inside of the Earth, from scratch, in your field, starting with a pencil. This is either the most brilliant thing you've ever attempted or the most delusional, possibly both. There's only one way to find out. Step 1. Survive. You know this part by now. Food, water, fire, free time. No great discovery in human history was made by someone starving in a field, and this one won't be either. So you solve survival first. You farm. You store food. And for the first time, you have something more valuable than carbon right now. The freedom to think without desperation, clouding every thought. Now you start studying what heat and pressure actually do to materials, not casually, obsessively. You watch rocks change under intense fire. You notice that materials behave completely differently when pushed beyond their normal conditions. They melt, they fuse, they transform into things they weren't before. This is the science of materials under extreme stress, and it will take you years to understand properly. But every year you spend understanding, it brings you one step closer to rearranging that pencil. Here's where the real story gets shocking. The first human being who successfully grew a real diamond in a laboratory didn't accomplish it until 1955. Not ancient times, not even a century ago. 1955. the year color television was introduced. A Swedish scientist named Anders Kumper figured out that if you take graphite, surround it with metal catalysts, specifically iron, nickel, or cobalt, and crush everything together at pressures of 5 to 6 gigapascals while heating it to between 1,300 and 1,600 degrees Celsius, something extraordinary happens inside. The graphite dissolves into the molten metal. Carbon atoms, now free and mobile, migrate slowly through the liquid metal toward a tiny seed crystal positioned at a slightly cooler spot in the chamber. And there, atom by atom, they begin rebuilding, not as graphite, but as diamond. The crystal grows over days to weeks, locking each new carbon atom into that rigid three-dimensional lattice, until you open the chamber and find a rough, yellowish crystal sitting exactly where a piece of graphite used to be. This method, high pressure, high temperature, or HPHT, essentially squeezes graphite into diamond using a machine that recreates the conditions 100 miles underground. The pressure involved is roughly equivalent to balancing the weight of a small car on the very tip of your fingernail. The heat is almost 3 times hotter than molten lava. The machine that generates these conditions is enormous, expensive, and unforgiving, but it works every time. Then, in the 1980s, scientists discovered something even stranger, a second path to diamond that uses zero pressure at all. Instead of crushing carbon, you dissolve it. You fill a sealed chamber with methane gas, the exact same gas burning on your kitchen stove right now, and you fire microwaves so powerful they tear the methane molecules completely apart. Carbon atoms, suddenly free and chaotic, drift downward through the plasma like atomic snow and land gently on a tiny diamond seed crystal positioned below. They attach, one invisible layer at a time, slowly rebuilding the diamond structure from the surface upward like the world's most patient and precise three-dimensional printer. This process, called chemical vapor deposition, CVD, runs continuously for 2 to 6 weeks. The diamond grows at roughly 1 to 10 micrometers per hour, slower than watching paint dry. But the diamond that emerges is so pure, so structurally perfect, it belongs to a category that only 1 to 2% of naturally mined diamonds ever reach. So you have 2 paths. The first mimics the Earth: extreme pressure, extreme heat, metal catalysts, weeks of waiting, and a rough diamond grows from graphite. The second mimics the stars: plasma, gas, layers of carbon atoms settling like silent snow onto a seed crystal that slowly becomes something breathtaking. Both start with carbon. Both end with diamond. Both work every single time. You take your pencil. You refine the graphite inside to a purer form. You build your pressure chamber, your heating system, your metal catalyst bed. You place the graphite inside alongside your tiny diamond seed, seal it completely, and push everything to its absolute extreme. Then you wait. Days pass. You can't see what's happening inside. The chamber is completely sealed and completely silent, but inside, carbon is dissolving, migrating through molten metal, and rebuilding itself bond by bond into a structure it has never naturally formed at the surface of this planet. You have to trust the chemistry completely. Then you open it. Inside, where graphite used to sit quietly, is a rough crystal, yellowish, unpolished, unimpressive at first glance. But you cut it, each facet angled precisely to redirect light. You polish every surface until it catches the light from across the room. And when the last facet is finished, light enters the stone, and something happens that never happens with graphite. It bounces inside the crystal, splits into every color of the visible spectrum, and comes back out of the top as a brilliant, flashing, unmistakable diamond. Here's what the diamond industry has spent decades hoping you never figure out. The stone that just came out of your chamber is chemically, physically, structurally, and optically identical to a diamond that spent 1 to 3 billion years forming 100 miles underground. Professional gemologists with specialist equipment can tell them apart. Your eyes cannot. An engagement ring made from a lab-grown diamond and one made from a mined diamond look exactly the same, feel exactly the same, cut glass exactly the same, and will last exactly the same, forever. The mined diamond costs 10 times more because it's rare, because it's hard to dig out of the ground, because a century of marketing convinced the world that the difficulty of getting it out of the earth is what makes it romantic, not the material itself, the difficulty. But the material, carbon, the most abundant element on the planet. It's in the air. It's in your food. It's in every living thing that ever breathed. And it's in the pencil on your desk, sitting there, waiting, completely unaware that the only thing separating it from a $10,000 diamond is pressure, heat, time, and someone patient enough to provide all three. Natural diamonds took 1 billion years. Yours took 3 weeks and a graphite pencil. The pencil was always a diamond. The earth just never told anyone.